Today on The Future of Everything, the future of artificial intelligence. Now, artificial intelligence, or AI, is on the minds of lots of folks these days. Some are wondering how AI can help their company or their organization be more competitive by improving the products, reducing costs, making things better. Others are worried about AI taking their jobs or making their jobs unnecessary in this time when we're hearing about AI capabilities that are at times very remarkable. The fact is that AI can do some things very well these days. For example, it can look at images or pictures and identify what's in the picture. It can write captions about the picture. It can find similar pictures and even understand what's going on in the picture. It can understand most of what we say when we speak. This is how our phone assistants and other things can listen to us and respond with the basic information that we're asking. More generally, if you give it lots of data, it can learn patterns in that data that allow it to make pretty good predictions and recognition of what's going on. But it needs a lot of data, typically, and the predictions are really only as good as the input data. What I mean by that is if the input data has biases built in, then some of the predictions may also have those same biases, whether you want them or not. In most cases, it's successful in pretty narrow areas where it does specific things that are. Now, there are dreams, we'll call them AI dreams, that are pretty far away still, like a general robotic assistant who can do whatever you ask, make you a sandwich or go do your errands. Professor Chelsea Finn is a professor of computer science and electrical engineering at Stanford University, and she works on AI and robotics techniques to try to create these generally useful AI systems that perhaps do not need as much as data as currently required and can perform tasks that maybe they can't do yet. Chelsea, you recently showed that you could create an AI system to help grade student computer programming projects. And it gives them hints about where they may have made mistakes and where they have introduced errors into their code. How did you build this system, and what does it tell us about the next generation of AI systems?
Yeah, great introduction and great question. So we're building a system to try to give feedback to students. And one of the things that's very challenging about this problem is that unlike a lot of applications of AI, you don't have a massive data set of students answering a question and having feedback for that exact question. Curriculum changes over time and the students change over time as well. And so we need a system that can adapt with small amounts of data for a given question. So for this problem, we use techniques called meta-learning to—
It's meta-learning.
Meta-learning, yes.
Right.
Learning how to learn, learning how to quickly learn on a set of past data so that it could very quickly learn how to adapt to a new problem and new students.
So tell me, I said grading, but I don't actually know. Were you actually grading papers, or was it more like helping the students see where there were problems?
It was more like the latter. It was giving feedback to students and giving them, like, pointing out errors or misconceptions that they made. And it wasn't actually counting for any sort of grade. It didn't have any implications on like any sort of final grade that they got. It was mostly just trying to help the students understand what they were learning well and what parts of the subject area they were not, they needed more learning.
Yes, and I know there's been some attention paid to this work in the press, and there was one story about at least one student who said that the feedback that it got from the AI system was exactly, I think it was him, exactly what he needed in order to then get over that hump and make the assignment work. Can you tell me a little bit, for the lay audience, what is meta-learning? Because it sounds great. In my introduction, I was talking about how a lot of these systems are famous for requiring tons of data, and it sounds like meta-learning is part of the solution to maybe needing less data. So what can you tell a layperson about meta-learning?
Yeah, there's a few different ways to look at it. One way to look at it is that rather than training a system to do one very narrow thing, like recognizing between cats and dogs, meta-learning algorithms try to study lots of different problems and try to learn kind of the common structure among all of those problems so that when they see a new problem, they can leverage their previous experience on past problems to very quickly solve that problem. And it essentially takes the level of machine learning up a level. Instead of learning to pattern matching for individual data points of a task. It actually pattern matches at the level of tasks, and it learns how to very quickly solve a new task.
So are you able to use, so you said that, assignments change, of course, and other things, people change. Are you able, however, to do this meta learning on the old data, like the old assignments from previous students, and still make it relevant to the new assignments? I guess the human mind kind of makes the same kind of mistakes over and over again. So it does make sense that maybe you could teach a computer not how the student is going to make errors for this particular assignment, but the types of errors that any student might make in any situation. Is that kind of the general idea?
Yeah, exactly. And we trained on previous historical data from the same course, from previous students taking the same course, and from previous instantiations of exams and homework assignments, so that for a new instantiation of the course with new students, it could quickly adapt.
So as long as we're talking about the grading, because I know you do many more things than that, but let's just to stay on that topic. How did it go down with the students? I did read about the 1 or 2 students who were quoted in the news items, but I guess there's so many questions. Did the students appreciate it? Are they not getting some sort of human touch that they would get otherwise? So how was the response and the reception to this among students?
Yeah, we were quite nervous about this before we deployed it. And I should emphasize that the instructors of the course were a huge part of the course. We were not replacing instructors. We were helping them give feedback on a diagnostic that they weren't able to give feedback on in the previous iteration of this very large online course. And the students, they were actually quite eager to get the feedback, and we asked them how useful the feedback was. We asked them if they agreed with the feedback from the system as well. And overall, the reception was actually quite positive. We were quite surprised, actually, that they actually agreed with the AI system more than they agreed with the human feedback. They also, anecdotally, they liked the tone of the feedback. And they appreciated that we kind of took the predictions made by the AI system and paired it with some feedback written by a person that was very friendly, and they really appreciated the friendly feedback. And in terms of the usefulness, we asked them on a score of 1 to 5, how useful was it for them? And I think it was an average of like 4.6 out of 5 in terms of usefulness.
So that's that's quite remarkable, actually, because that and I guess I didn't say, but part of the vision for this is that these are some very, very large classes where just having a teaching staff to give personalized feedback would be prohibitive. So how big are the classes that you kind of rolled out these technologies in?
So we rolled this out for a class called Code in Place, which had actually thousands of students.
Wow.
And it was a free course that was taught during the pandemic. I think that in the future, we'd also love to apply it to slightly more normal sized courses, like college courses with hundreds of students, where instructors are spending a lot of time trying to give this personalized feedback. And if the system can help them give it more quickly, give it more accurately, then they can spend more time on other parts of the course and providing high quality instruction.
And the other question that I have to ask, I want to ask, and I have to ask, is about the ethical dimensions and the privacy dimensions. Does that come up? I mean, I don't immediately see a big problem, but I could imagine a student, protesting that, wait a minute, now there are computers that are storing information about the kinds of mistakes that I make and how well I responded. Is this going to contribute to a profile? I'm making this all up, but are those indeed issues that have to be confronted? And if so, how did you maneuver through those issues?
Absolutely. These are things that we're extremely careful about. One thing is all the data that we use is stored in a very secure way, and it's not publicly available. And this is good from a privacy standpoint. It's somewhat unfortunate, actually, from the standpoint of machine learning, because if people had access to this kind of data, then we would be able to make more progress on the problem.
Yeah.
And we're trying to look into ways that are that would allow us to produce data that could be released in a way that is ethical. And then another concern is bias in the system as well. And in this case, we didn't expect there to be any bias because it's looking at typed programming code. It's not looking at any comments that the student wrote. But we also checked for bias, both in terms of gender and different geographic countries that the students were from. And we didn't see any signs of bias in the data that we looked at.
Did you have to, again, just because I find this so interesting, did you have to get some sort of human subject consent to run this study? And was there control groups who didn't get the intervention and some who did, or was it a little bit more everybody gets it and let's see what happens?
Yeah, so Chris Peach, who was one of the instructors and my collaborator on this project, one of my main collaborators on this project on the education side, he went through the process of getting IRB approvals for running studies in all of his courses, essentially. Different IRBs for different courses, but he went through that process to make sure that that it was approved at that level.
Yeah, great. Okay, so I know that you do much more than automated systems for helping people code, and I know that you do a lot of work in robotics. And so tell me about the types of robotics that you're interested in improving. We know robots are on people's minds these days. I think self-driving cars, you could argue, are a form of robot, and then there are many others. So tell me about your slice of the robotic world and what are the problems that are driving you, so to speak, driving you in your research?
Absolutely. So I guess similar to the education scenario, I'm really fascinated by allowing robots to solve many different things, not just one narrow thing. And actually, some of my research on robotics inspired my work on meta learning, which led to some of the work in education, because it turns out actually a lot of the problems are not all that different. As one example of a problem that I would love to solve is just having robots be able to do something as simple as walk into a new kitchen and make a bowl of cereal. This is such a dumb and basic task for people. It's so like we can do this in our sleep almost, but it's actually extremely difficult to produce this kind of behavior in robots. And I'm really fascinated by this ability to go into new environments, do new tasks, and interact with new objects. It's this kind of generalization.
Right. And so I know that one of the big terms that comes up just reviewing some of the papers that you have written is this idea of reinforcement learning. And I don't think people necessarily understand what that is. So could you give us a little tutorial about reinforcement learning in machine learning, what it is, and then why it comes up so much in this robotic work that you described?
Absolutely. Robots are typically, I guess there's a few ways that you could try to think about generating robot behavior. One is to try to program the robot's exact motions, but that gets very difficult when the environment becomes unknown, where you don't know where objects are and so forth. Reinforcement learning tries to allow robots to acquire behaviors through trial and error, through experience, where they attempt to solve a task and use that experience at trying to solve the task to improve the behavior and get better and better over time. So kind of like how a human might learn how to do a backflip by kind of trying iteratively and learning from mistakes, we want robots to be able to learn from experience and learn from their mistakes as well.
Yeah, and that actually is that makes perfect sense. Is that, you know, when you try something and fail, you kind of do a little inventory of what you tried. You typically don't try it identically the next time because you already know that that's unlikely to work. And so you could imagine perhaps getting a robot to try it a little bit differently next time, and then they still need to, I guess, understand whether they succeeded or failed. And so, but maybe that's, I guess I'm making this up, but maybe your main test becomes in telling them when they've succeeded and when they failed, and then giving them a toolbox of ways to try. So is it indeed the pouring a bowl of cereal? Is that something that's on the horizon, or do you have to take some steps back and do much more basic things first?
Yeah, great question. It actually depends a lot on how you set up the problem. If the robot has been able to practice with that bowl and with that carton of milk and with that particular cereal box, and it's in a single environment, like it's a very narrow setting, I think that that's something that we may already be able to do. It's when things become more varied that it becomes more difficult. When the robot needs to interact with new cereal boxes, or it needs to be able to interact with new bowls or new environments, or and so forth. And really the kind of variety that the robot has to be able to handle makes is what makes the problem potentially more and more difficult.
Yes, no, it's great. I love this example because now that many of us have stayed at Airbnbs, this problem has become a real problem. Like you go into a new kitchen, and we're probably going into a lot more new kitchens. Well, maybe not with the pandemic, but before the pandemic, I probably walked into new kitchens way more because of, renting somebody's house for an Airbnb. And then it's like, okay, where's the pantry? Where's the milk? Where's the spoons? And so that's the kind of search that a robot would have to do. Does this work? Do we have the physical robots to do these kinds of things? So, you've described that we might be able to do in a very controlled situation. What is the status of the hardware of robots in terms of being able to be the right size and maneuverability for these kind of everyday tasks?
I think that we absolutely have the technology and the hardware that can accomplish it. The hardware is very expensive. Some of the robots that we work with are tens of thousands of dollars. And if you want kind of a full humanoid style robot, that can get much more expensive. But we have the technology. And I think that at the level of the technology, the software, the brain of the robot is really what's lacking.
Are you driven? So the next question that I had was, are there particular applications? So you said, you pointed out this application of pouring a bowl of cereal, which, as you said, is very trivial for humans. Are there areas of application that you focus on where you see that there would be an appetite for that sometime soon, where the market, so to speak, is looking for that kind of capability? I don't know the degree to which you're driven by these kind of goal applications versus more kind of an open-ended research program.
Yeah, so I'm a little bit more motivated by open-ended, really long-term challenging problems, but I do think that there is a market for some of this research already. I think that the biggest market is in more controlled factory-like settings, like in manufacturing and logistics, where the environment is a little bit more controlled. And so you have a little bit less variability, like I was talking about before. And when you have a little bit less variability, the robot doesn't have to handle quite as many possibilities in the world. And these systems are more successful in those kinds of settings.
Are there industries that are knocking at your door more than others? So you just said logistics, are the Amazons of the world and the Walmarts of the world, are they looking at this? Or is it more like the Roombas and the automatic vacuum cleaner companies? I'm just wondering, because when your work comes to their attention, I'm sure you get calls, and I'm wondering to the degree you can you tell us what kind of calls you're getting?
Absolutely. I think that Amazon is particularly interested in this kind of technology, and they actually run challenges at the robotics conferences on a regular basis. They've had the Amazon picking challenge, for example, where they set up something that looks a lot like their warehouses, and they say, robotics researchers, can you solve this problem? And so they're an example of someone who's extremely interested in this technology.
Great. Well, this is The Future of Everything. I'm Russ Altman, more with Professor Chelsea Finn about robotics and its future, next on Sirius XM. Welcome back to The Future of Everything. I'm Russ Altman. I'm speaking with Professor Chelsea Finn. We're talking about robotics, the future of robotics, and different kinds of machine learning. I wanted to ask about self-driving cars. These are kind of a form of robot, and I know that you have some ideas and interest in this. So what is the status of self-driving cars, and are the meta-learning and reinforcement learning technologies that you described earlier, are they helping in making this be a thing?
Yeah. Self-driving cars is actually, there are parts of the problem that are quite easy, and there are parts of the problem that are extremely difficult. Actually, I would reason to say that 99% of self-driving cars is actually not that hard, like lane following, for example, and understanding when a light is green, that stop signs, that sort of stuff comes up all the time, and that sort of stuff is pretty easy. Mm-hmm. The hard part about self-driving cars is the rare situations that will inevitably come up, where a bird flies in front of the camera of the car, or there's a construction zone, or there is just this huge variety of these kinds of situations. Maybe there's a stop sign on the back of a bus, for example. That doesn't mean that you should necessarily stop.
Right, right.
You essentially, to solve these kinds of problems, you need some form of common sense. And building really intuitive common sense into machines is extremely difficult, and it's potentially one of the most difficult parts of artificial intelligence. And this is potentially unfortunate for self-driving cars, because it means that while we can solve 99% of the problem, that remaining 1% might be extremely difficult. And it might be that we can't deploy these technologies until we solve that 1%.
You know, I'm very interested in what you're saying, because I know that a lot of these companies are putting cars out on the road and they're hoping to come across these rare events in order to like increase their exposure. But I think the way you just said it makes it clear that that might not be the best strategy, because even if you leave a car out there forever, you can, whatever it's seen, you and I can easily come up with scenarios that it hasn't seen where it would need to behave properly. And then I think back on what you were saying about the looking at computer programming assignments, and I see a little connection, because you said you weren't able to imagine, you didn't have enough data for every possible mistake that they could make on this new assignment. So you had to learn how to think about it more abstractly. So I'm going to guess that you're trying to think about similar approaches for the self-driving cars.
Absolutely. I think that if we can quickly adapt, I think that when we see a really novel situation, I don't think that humans know like immediately exactly what to do. If you think about it though, for a little bit, you realize, okay, this is probably there for this reason. And so if you can very quickly adapt, then, and use kind of a second of experience or something from that new situation, you might be able to do better. You might be able to handle that really long tail of situations.
So I don't know if this is true, but I've had the impression that the claims about self-driving cars being right around the corner, no pun intended, are being pulled back a little bit, and that this has turned out to be a little bit harder than some of these companies thought. This might be wrong, and that's why I'm asking. Is it the case that we're seeing a little bit of a reset and people saying, you know what, we're going to need to slow down expectations about the rollout of self-driving cars because of this exact problem?
Yeah, I think that we are seeing a slowdown of excitement and trying to lower the expectations a little bit. I think that the kinds of scenarios where we might be able to expect it being rolling out is in like a small region where you have lots of data, and where perhaps these rare situations are less likely to arise. I think that they are going to arise inevitably in any environment, but I think that there is potentially a little bit of hope when you have a very narrow region and you've been able to collect a lot of data in that region.
Right. So it might be very local areas where they have confidence that they've seen almost everything. And then they have confidence that they're fail safes for like, just stop the car because you have no idea what's going on, or whatever. Those policies need to be developed. I know that a lot of your work, just switching topics, a lot of your work is in this area of distributional shift, which is very technical, but my understanding of it is that when you train an AI system using data, it's kind of assuming that when you deploy it, the data that it sees in the future will be a lot like the data it saw in the past. And if it doesn't, if the new world is very different from what it was trained on, it might have erratic, unpredictable, or wrong behavior. And so have I characterized distributional shift correctly? It sounds like it's a big problem. And so what are the approaches that you're taking to try to address this problem?
Yeah, you've characterized it correctly. And to give an example, in the self-driving car case, if traffic patterns change in some way, if school buses start bringing people to school at a certain point in time, you didn't see that kind of data before, this is when these machine learning systems can start to fail.
Yes.
And I think this problem is super important because it comes up in self-driving cars, but it comes up really in any sort of application where you train on data collected in the past and you ultimately want to deploy the system on data from the present.
It also strikes me, just to add to that, that once you start using a self-driving car, it will be contributing data that's going to be very different perhaps from when there were no self-driving cars, because it's going to be seeing all these other self-driving cars. And so we can guarantee that the distribution of what it sees will shift once this becomes a common. So, okay, so that we know what the problem is, what are the solutions?
Yeah, I think it's still an open problem. And that's one of the reasons why I'm really excited about working on it. We have some solutions to it. There's some approaches are to actually try to adapt to the distribution shift, to take a tiny bit of data from the new distribution and use that to try to do better. Mm-hmm. Similar to what we were talking about before. Another approach is to try to be pessimistic about the kind of data distributions. And typically in machine learning, you try to train in the average case across your data set. But instead of training for the average case, if you instead train for the worst case, then your system might be more prepared if something changes. And so actually there's some pretty neat objectives, actually train machine learning systems to prepare for the worst rather than to prepare for things on average.
Oh, so could you just say more about that? Because that I haven't heard about that, and it sounds very interesting. So the pessimism is not so much the researcher being pessimistic. I saw it in one of the titles of one of your papers, but the pessimism is actually the way you set up the AI is to not assume. So I guess my question is, tell me exactly where and how you might introduce pessimism into an AI system, because I find that fascinating.
Yeah, so the idea is to be pessimistic with respect to the data. So if there are parts of the data distribution that you are bad at, then you want to practice those cases, because if you're pessimistic about what's going to happen, then what might happen is that in the next data distribution, those data points are most of your distribution, most of the data that you see. And so if you train on the things that you're bad at, then you're preparing for the worst case case data that you might see in the future.
And then of course you can say, look, I don't want to have terrible performance on the average case or the best case, but I'm willing to give up perhaps a little bit of performance in those cases in order to make sure I do okay on these really bad ones.
Yeah, exactly.
Have there been any experimental results showing that this actually can work?
Yeah, there have been. They're still in somewhat simple settings like image classification systems or trying to predict toxicity from comments that were taken from the internet, where you want to upweight the ones that you're not very good at, maybe from demographics that are a minority of the data set.
Right.
And we've seen that these systems do better in the worst case. They're better able to handle distribution shift than standard systems.
Yeah, I love this idea because, as a technologist and as a scientist, you always want to hope that your technology is going to be great and that it's going to help change the world for the better. But this idea that, okay, let's just focus on what we do poorly, because we can probably learn more from that than just reveling in how well we do on the easier cases. So that's a very attractive approach. Well, in the last literally 1 minute, I want to ask you for just some prognostication about how this is all going to go down in terms of the timescale with which robotics will start to be seen in the home, in the workplace. You already made a reference to Amazon. What's the prognosis for robotics in 30 seconds?
Yeah, I'm quite pessimistic, actually. I think that we won't start seeing robots in homes beyond your Roomba. For example, if they need to touch objects, if they need to interact with objects, I don't think we're going to see them in the home for at least more than 5 years, if not more than 10 years, simply because the amount of variety that they have to deal with in homes and offices and so forth is a lot. And it's tremendously difficult to create these kind of robots that can handle that variety.
Well, thank you. And thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.